In this video, I will write a proof for the mean value theorem. I already explained the statement in the previous video, so this one will only contain the proof. To begin, let's recall the statement. I start with a function f defined on an interval ab, including the endpoints. If f is continuous on the full interval and differentiable on the interior, then I can conclude that there must be a point in the interior where the derivative takes this value. Before I write the proof, as preparation, I will draw a graph and try to explain the idea of the proof pictorically. Once we understand the idea, writing the proof will be easier. Here is the graph of a function defined on the interval ab. I want to use Rolle's theorem to prove the mean value theorem, but Rolle's theorem only applies to functions that take the same value at a and b, so I cannot use it directly on f. My plan is to construct a second function on which to use Rolle's theorem. The second function, which I will call h, is the following. Given a generic value of x here, h of x is the vertical distance between the red line and the graph of f. Notice that h of a is 0, and h of b is also 0, so I will be able to use Rolle's theorem on h. To write the proof algebraically, I will need an equation for h. I can write h of x as this vertical distance minus this vertical distance. Since this is x, the y-coordinate here is f of x, so I can write this vertical distance as f of x minus f of a. Now this piece here is x minus a, and this vertical distance is m times x minus a, where m is the slope of the red line. But the red line is just the line going through 2 points on the graph of f with x-coordinates a and b. So we know that m equals f of b minus f of a over b minus a. And now I can write h of x explicitly as this quantity minus this quantity. So h of x equals f of x minus f of a minus m times x minus a. And now I am ready. Here is my plan. I begin with a function f. I construct a second function h by this equation. I apply Rolle's theorem to h. That will give me some conclusion about its derivative h prime. And whatever that derivative is, I transform it into some conclusion about f prime. That's the idea. Let's do it. This is just a reminder of the statement of the theorem. To begin the proof, I am going to call m the quantity f of b minus f of a over b minus a. I did not need to give it a name, but I do not want to have to write the whole thing all the time. Now, I define a new function h on the interval ab by this equation. H of x equals f of x minus f of a minus m times x minus a. I want to apply Rolle's theorem to h on ab. Before I can do that, I need to verify the 3 hypotheses of Rolle's theorem. First, h is continuous on ab closed because f is continuous on ab closed, and h is simply made of f, constant terms, and polynomials. Similarly, h is differentiable on ab open because f is differentiable on ab open. And finally, h of a is 0. Just plug x equals a in the definition of h. And h of b is also 0. This requires using what m is. Excellent. So I am allowed to use Rolle's theorem on h. I conclude from Rolle's theorem that there is a number c between a and b such that the derivative h prime of c equals 0. But look at the definition of h. For any value of x, h prime of x is simply f prime of x minus m. Therefore, h prime of c equals 0 is the same as f prime of c equals m. And that is exactly what I was trying to show. This completes the proof. We are done. Excellent. After all this work, we have a proof of the mean value theorem. We are now ready to start profiting from it.